got to keep in mind, these are the people that tend to get this disease are the go-getters. They're the senior corporate executives that are really high functioning, that a lot of times they're in great shape and they'll say they jog 10 miles a day. I mean, it's just incredible what they used to do prior to getting this. They would have a flu-like illness, and then suddenly everything fell apart. They never recovered from it. And it was like a perfect storm of events that occurred. A lot, some of them report they had a lot of stress going on in their life at the time. Then they also had the virus come in, and the two things, along with other problems that were occurring at the same time, just the body wasn't able to recover after that.
I'm going to wait until you've done this, but until I've seen what you're saying. But you're reminding me immediately of long COVID and the questions that we should be asking around long COVID. Who collapses to this virus? What are the conditions under which that happens? And where's the immune system? And is this really a disease? All of those are, to me, really questions that you're already raising, and I'm fascinated. So keep going.
That's a very good point. And there is a lot of shared overlap and similarity between these two diseases. And long COVID patients do report a lot of the things we're talking about. The hope is that if we solve, a lot of people are working on what's going on with it because they don't understand why this is occurring in patients. And some people are not able to get past this disease and not able to recover, even though now it's been going on 2 years for some folks. So it's starting to look like that they are developing a chronic condition from that initial infection. And the good thing about that is we know where it started. We know in ME/CFS, it could be any infectious pathogen virus. Usually they expected, a lot of them suspect Epstein-Barr, Herpes Symplex virus, one of those etiologies that triggers it. But it's variable, right? And at least with COVID now, we have this, we know a lot about the virus. So we know at least that is an unknown that we don't have to deal with. And so the hope is that by solving long COVID, that will also help us to also apply or provide a template for what to do with ME/CFS, at least for some patients. But we'll be able to figure out what to do with them. It is probably one of the few silver linings in this pandemic. Unfortunately, it took a pandemic for this to become a prominent, front center issue, right? And unfortunately, it's going to continue to grow. It's going to continue to get even worse as the virus mutates and as there's more exposure and more people getting it. And now even people with mild symptoms they're not hospitalized, but yet they're experiencing long COVID symptoms that are so similar to what the type of things you get with ME/CFS. So I'm interested now in conducting studies that compare these two groups. And that's what we have put in a grant application to NIH to look at that, working with some collaborators at Northwestern University who do all the other modalities except for EEG. I do the acute EEG, and then we take all that and combine it. So there's hope that will get funded, and if so, then we will have the funds to do a large study and really go after this once and maybe figure it out once and for all. Because I think that there's hope that it's going to be at least leading to a treatment. That's the idea. There's no treatments for this disease. Basically patients' palliative care is basically all we have. And different patients find different treatments that work. It's a mixed bag. You'll find acyclovir maybe for some folks, and then other folks, they take it doesn't do anything. For example, so. Hi, this is Dr. Mark Zinn with the NeuroCognitive Research Institute, and you're listening to the NeuroNoodle Network podcast.
Welcome to NeuroNoodle's Neurofeedback and Neuropsychology podcast featuring our neuropsychologist, Dr. Leonard Jason's tech whiz, neurofeedback legend Jay Gunkelman, and author of Neurofeedback and the Treatment of Developmental Trauma, Sebern Fisher. Our goal is to provide information, promote options for better mental health. This is an all-star cast, and I'm more than happy to share their knowledge with you. Hey, my name is Pete, and today we have a very special guest, Dr. Mark Zinn, director and co-founder of the NeuroCognitive Research Institute. But before we get to Dr. Zinn, we have some Patreon love to dish out. We'd like to thank our Patreon business supporters, as well as our show sponsor. Mary Tracy's Neurotraining Strategies offers a higher standard of EEG, QEEG education to EEG clinicians, technicians, and neurofeedback practitioners with convenient online BCIA and QEEG certified didactic courses. Hey, 3 things that our listeners and viewers can do to help us spread the word of neurofeedback. Number 1, please subscribe to us on YouTube. That little action turns 3 people from learning about neuroscience and neurofeedback to 3,000. I don't know anything about algorithms. All I know is that little action right there makes the pie even larger. Number 2, please give us a review on whatever platform you listen or watch us on. Hey, we'll take 5 stars on Apple Podcasts, but Sebern will even accept 4.5. If you have the means, please support us on Patreon/NeuroNoodle. There are different levels in which you can support, whether you're a mom or dad or a clinician. There's even an option where you can have your own Q&A with Jay Gunkelman. Hey, the support helps us improve the quality of our content. Okay, let's talk with Dr. Mark Zinn. Thank you so much for coming on the show.
Thank you for having me. Pleasure to be here.
You're a good Chicago guy, DePaul guy. I'm in Chicago too. I don't know. I kind of talk funny, people say, or maybe you guys talk funny. Please tell us about your background and how you got the NeuroCognitive Institute going. Yeah,
my wife and I, my late wife and I founded the NeuroCognitive Institute in 2015. And we were interested in using QEEG to study an illness known as, it's a long name, Myalgic Encephalomyelitis, chronic fatigue syndrome. So we just say MECFS. That's the name of the disease or the disorder that we were interested in studying. My background is that I was originally wanting to become a concert pianist, and I actually went to school, in music school, in piano performance. So I dealt with a lot of issues in psychophysiology dealing with performing on a solo piano recital, which is considered very demanding because you have to recite basically 186,000 notes in 75 minutes and try to get an error term down to near 0 doing that, which is really stressful. Okay. And you're doing that before an audience. That's also stressful. And then you're dealing with the physiology, and that's interrupting the performance. Mm-hmm. So by that process of doing that, and also teaching as well, because I was also a teacher, and I still continue to work with students, that process made me become very interested in psychophysiology, which led into neuroscience, because we were also interested in the brain and how the brain was changing in accordance with music learning. So we had our Lexicor NeuroSearch 24 system in the early 2000s. That was one of the first ones to come out. That was our first system, and we used that. We used that with we had a lab school, basically, with our piano students, and we found a bunch of interesting findings for that concerning music learning and performance. And we did that for about 10 years. Through the exposure to young children over time, particularly Marcy was susceptible to getting infections from them. There was transmission of certain pathogens, and a lot of it was viruses, things like that kids would bring in. Over time, Marcy developed the condition of, she was diagnosed with herpes encephalitis, but that really turned into MECFS. And what we didn't understand at the time was what that meant. We had never even heard of CFS before. We didn't know what it was about. So we went, and it was a serendipitous thing that happened. We met Dr. Jose Montoya at Stanford through Marcy had actually been bitten by her cat. So the cat bite led to her meeting with this doctor, Jose Montoya, who is the head infectious diseases doctor at Stanford Hospital. They were worried about her hands because she was bitten on the hand. It swelled up like a balloon. And so he got in a conversation with Marcy. Marcy was telling her about her background. And he said, I'm doing this MECFS initiative, and I need and you do EEG, and I'm really looking for someone like you to head up an EEG project within that. Would you be interested in doing that? And she says, oh, sure, that would be great. I would like to do that. So that's how we got introduced to ME/CFS. By the way, he did diagnose her later on with ME/CFS. So that made sense to me. So I got a firsthand view of what it's like to have this illness. I think you need that in order to study it. If you don't have a firsthand relative or someone that you live with that has it, I don't think you really grasp what's going on, because there's really a lot happening with this illness, and it's very hard to define. So
let me just clarify. You are talking about chronic fatigue syndrome. That's what people would call it regularly, right? It's the same.
It goes by several names. The CDC named it chronic fatigue syndrome. I think it was back in 1994. Later on, that name became questioned because it didn't really capture the illness. Prior to that, it was called myalgic encephalomyelitis. Patients liked that term. It sounded more like that was really what was capturing the essence of the illness. So there was a kind of a compromise. It became ME/CFS, which is so much easier to say, of course, than the other thing. I mean, I don't know how many syllables that is, but and then in 2015, the IOM committee at NIH decided to rename it to systemic exertion intolerance disease, so SEID. So, but nobody's really adopted that. Now, I mean, I don't think so. So we don't really discuss it, but it's not really about fatigue. That's the issue. It's about exertion and post-exertional malaise that happens when you engage in an activity for a brief period of time. There's no biomarkers. The diagnosis is by exclusion. They use a case definition to diagnose this. So that means that you get ME/CFS is really an umbrella term for probably a lot of clinical subtypes going on in that you can't really get a pure sample of patients when you're studying it. The issue was that there was a lot of mixed findings in the literature, which led to a lot of confusion. There was some of the studies didn't have very good sample sizes. Some of the studies, they just weren't able to get the right group, or that a lot of them had in this sample a subsample of those patients that did have findings, and they didn't have. The ones that did have findings were the ones that they tended to not have comorbidities, and so that was interesting. Like, for instance, depression, because a lot of people think this might be depression. Depression has a lot of overlap, and more we're developing new technologies to study this illness, but we haven't really figured out a great way to do this yet. And we haven't figured out a great way to study two things: cognitive impairment or brain fog, and then post-exertional malaise. Right? Those are two separate things. They go together. What I did was and Marcy and I did was from our EEG study at Stanford, we got some really interesting findings using QEEG and eLORETA. What we were able to do was show that there was abnormalities going on in a really large patient sample, because they had a very large patient sample. It was a case control study, so we were able to compare cases with controls, and we were able to use QEEG eLORETA to do that, and we found some really interesting findings that explained what was going on with their fatigue. And with that, we decided that's what led to founding this institute. That's really what led us to do it. We thought, okay, we've got something here, a modality that can actually, has the capability of picking up on the subtle changes that are occurring in the brain, because that's really what's happening here. The patients are not being, with fMRI, which has its own limitations, as we know, it's not able to pick up on the subtle changes that are taking place. QEEG, however, it has this high time resolution, right? It has the ability to look at the activity of the brain on the millisecond time scale, which is terrific, as opposed to seconds or longer with the hemodynamic responses, which, by the way, are not uniformly distributed across the brain. So we don't know for sure. The assumption was that certain areas of the brain were, getting the same amount of blood flow, but it turns out that that's not necessarily the case. So there's a lot of issues with fMRI that prevented, and for this particular illness, it really made it difficult to really get any findings. And in the neuropsych test, by the way, they did neuropsych testing on people, and they didn't really score that much differently from healthy controls. The patients were able to, either the test didn't capture what was going on because they're just not sensitive enough. Once again, they were able to rise to the occasion and do it. I mean, most of these patients are actually very functional in some ways. Even though they have the illness, they're actually able to perform okay. But the problem is that those symptoms change at any given moment and drastically, right? And so they can become very intense, very severe, and rapidly fluctuating. And they can't manage the illness because of that. So that's really what's going on with the neuropsych tests. They weren't able to really identify things all that well. fMRI didn't have the capacity. So EEG, as it turns out, might be one of the great tools for this particular illness. It's just suitable for this. It's ideal for this type of problem, to solve this type of problem. So that's why we found the NCRI to really go after this. And we moved from California to Chicago. I wanted to, go to school here at DePaul University, and that's where I got my Ph.D. And I, worked with Dr. Leonard Jason at the Center for Community Research, and we did some studies, and we were able to get some more interesting findings. That's what I'd like to share with you today at some point is to go over some of the findings we got. You can see what I'm talking about and how this relates to eLORETA, because eLORETA is really a very powerful tool that is telling you that not only that there's an abnormality, but where the abnormality in the brain or the dysfunction, the dysregulation in the brain is occurring. And so I think it's really important that this modality, and probably used with other modalities as well, there will eventually be a way to identify patients, that you don't have to just rely on case definitions. You're going to be able to differentiate patients. You're going to be able to see clinical subtypes. It's just a matter of getting enough patients in the sample and getting a large enough sample and having the funding to do it.
What does the great DSM-5 say about this condition? Is it something you can look in there and find it?
The DSM-5, well, this would be cognitive impairment due to a medical condition, and falling under that category. So it's not a psychiatric disorder, although there might be psychiatric comorbidity, which is understandable. If any one of us got a neurological illness, I imagine we'd be a little depressed about that.
Dr. Zinn, you have something to share with us, I believe. What do you have? I'm
just going to start out with the Stanford study, because that's really what prompted us to really go at this. And it's just, these findings are really remarkable, I think. So I'm just going to, let me just share the screen. This was a study that we did at Stanford. This was the project with the original project. This was the result of this manuscript here. It was published in Biological Psychology. So the interesting thing about the brain in this disease is it seems like that it's underperforming or hypoactive, and that fits with other findings as well. It just seems that the brain doesn't have the same amount of energy in it, that the allocation of the energy is not occurring in the same way, or there's just something that is not able to restore itself. What we did, we did this study. This was involving 50 patients with CFS, ME-CFS, and 50 patients with that were healthy. They weren't patients, they were healthy individuals, just doing a case control comparison. And what we found was, when we looked at the eLORETA, we found a really interesting pattern in the delta band. And this is what here. So this is a huge cluster. It's like 50% of the frontal lobe and 30% of the limbic lobe. Just looking all the yellow here in the frontal lobe of the brain. See, so in the prefrontal cortex, especially, where they're having a lot of dysexecutive problems going on. They're having problems with attention. They're having problems with decision making. These are all the things that, and setting goals, that they're having all these problems that do align with problems that are occurring in the frontal lobe. But this is a cluster analysis, and that's why it's all yellow like that. What this is to capture the size or the extent, the pathology that's going on in the sample. And this is in the delta band, which is very interesting, because that delta band, first of all, delta, excess delta is reported in, just the EEG, conventional EEG literature. It's been reported in long COVID or COVID-19 patients that are hospitalized. And it's been reported in, if you look at, chapters like in Niedermeyer and other EEG physiology books, you see there's a lot of inflammatory conditions do present with intermittent delta activity, frontal intermittent delta activity, things like that. So a lot of slow wave type changes going on in the brain. The problem is that in this disease, these changes are not visible to the naked eye. So you can look at the waveform. A neurologist can look at the waveform and say it's fine. And they'll give the report, they'll write the report, unremarkable, there's nothing going on, basically. And the patients are disappointed because they feel like, well, gee, I'm having all these symptoms. Yeah. Well, how could this mismatch occur? And it's just because they're not using computers to quantify the changes that are taking place. It's to say that, well, if it's not visible, then it's not there. It's kind of like saying, well, I can look at the sky and I can't see the planets, so they're not there. I mean, you gotta use some more equipment to get at that, right? I mean, that's why we have the space telescopes. We have, there's more in there. You got to dig for it, and that's really what a point I want to make is that subtle changes occurring in the brain can have big ramifications. It can have big potential for a lot of symptoms, because these symptoms appear to be all brain-based that they're having. The symptoms are really prominent, which I'm going to go into. So this is interesting. We also found this is the most robust finding, and again, this is just showing you the depth, right? So if you look at the depth here, it starts out in the rectal gyrus and in areas of the limbic system, and then it just gets higher and higher, and you can see how there's the orbital frontal cortex, the ventral prefrontal cortex, and the medial regions of the cortex, which are interesting, and the anterior cingulate, and other areas as well. Now we also found some other things like decreased beta activity in the it's called the parietal lobule, but basically in the sensory motor cortex, which is interesting because the patients are really having trouble with movement. They're much slower. They have muscle weakness. So this to me suggested, a diminished cortical drive for being able to execute motor movements, to be able to do their daily activities. It aligns with that. Also aligns with sensory perceptual issues that they're having. A lot of them are having problems with sensations that are going on, paresthesias, things like that. So that was really interesting, and those were the results of the Stanford study. We also found a cluster that was related to fatigue. This was in Brokaw's area, which I thought was interesting. So this was a focal region here, which was identified with we're using eLORETA, which found this focal. Again, this is in delta band. This focal region that on the left hemisphere, which happened to be right around the language centers. And so, a lot of them do, when you listen to them talk, that their speech is a little bit slurred, and they do have issues with word finding and other language-based issues. So I thought that was really interesting as well. And that was related to, we had a clinical measure of fatigue going on. So when you're talking to one of these patients, listen real carefully to their words because they're having trouble coming up with words that they're trying to formulate. They will stumble and they will say things incorrectly sometimes, and they will also sound a little bit like they've had one too many cocktails or something like that. So that's really interesting, this aphasia type occurrence, and that's something that hasn't really been looked at. We haven't really looked at aphasia in this illness at all. To my knowledge, there's not really any studies that really look at this. So interestingly, the insight that you gain from this modality and then the directions you can take from it, what this study led to other studies where I was wanting to look at the brain networks, because this is not networks, right? So we also used eLORETA, and this was published in the Applied Psychophysiology and Biofeedback Journal, and we were looking for the connectivity in the brain and how the regions were connected, and we looked at several major networks: default mode, salience, and executive functioning. There's actually the executive network. We looked at those three networks because they sort of function synergistically together. And there's a lot of other networks going on too, but we just had to keep it limited to those three for this particular study. It was a small study. It was a pilot study. It wasn't as big as the other one. So that was the other thing. But what we found was a similar problem in connectivity. Now, the blue lines are about to see. So this is the executive network, for example. So the edges in the network of the nodes that are, and comprised of this network are, they're blue, indicating that they're hypoconnected or they're disconnected. There's not as, when it looks at the synchronization between those two regions in all those vertices you see, the entire network is brought down basically in this disease. Now, this is something you might see in a disease like Alzheimer's. And it's not, I'm not saying this is Alzheimer's, but you might see something like this as the regions of the brain become degenerated and the tissue starts to become, dysfunctional or dying off. The cells actually start dying. You're going to have, obviously, those networks are going to get broken apart, that there's not going to be the same connectivity occurring, and you're going to see this sort of pattern. And and this was another network that's the same network. But see, this is the salience network. So looking at the salience network, and the salience network is it was a really important network that directs our attention to salient events that are occurring in our environment. And it has a lot to do with directing either internal or outward. So it can basically help us switch between our direction, our attention toward ourselves or toward the external environment, and that's the salience network at work. So it has a lot to do with homeostasis and maintaining homeostasis and things like that. And then here's the default mode network, and in the posterior regions of the default mode network, we found this connectivity same issue. So all three networks had, again, this is a smaller patient sample. I wish we had 50 people, but we didn't. But in this sample, patients compared to controls, we found this hypoconnectivity going on. So the hypo pattern sort of occurs here again, but in a different type of analysis, basically. Then what I did was I looked at network efficiency. I decided to let's just see what it looks like with the whole brain, right? We just do a whole brain connectome analysis, and let's see what comes up, in terms of the network. So we looked at the networks. We used a process called graph theory to examine something called small worldness, to examine how how efficiently are these networks performing, right? And so what this line shows is the healthy controls. Their networks are more efficient. This is closer to 1, see? As it gets down here, you can see this is significantly different. For CFS, for ME-CFS, their networks are less efficient. That's what this shows. This is in delta once again. I looked at delta and alpha, both those. In alpha, it was still that same trend, but not as prominent. It wasn't as pronounced. The most robust finding was delta once again. We were able to take a composite score of this is a subjective measure, unfortunately, of their own ratings but their ratings of their cognitive impairment. If you take, they rated their cognitive impairment, the composite score on those different impairments that were actually aggregated together. So you see the slope of the line going down. So as the score got higher, as the score increased, I should say, the composite score, then their small worldness score went down. It's just interesting to see that. And then in 2021, in 2021, I decided, okay, I shifted gears and decided, well, okay, so we're able to identify signs of cognitive impairment. We're able to actually quantify that. So maybe we should also look at PEM. And this has been a huge stumbling block in the field because nobody's really kind of figured out a way to really address this currently.
Say what are you addressing?
So it's called post-exertional malaise. And what this is, this is like the hallmark feature of the illness. This is what makes everybody wonder what's going on. So you could have somebody that seems perfectly normal. They're functioning. And then suddenly they crash. And for no real apparent reason, but they just have to stop what they're doing. So for my wife, it could be like we were just kind of walking through the store or grocery store, suddenly she would crash and have to go sit down, and then have to go into the car. I'd have to finish the shopping trip and check out myself. It was just really unpredictable what would occur. And so, okay, so how can we use QEEG to measure this? This is a reactivity of the brain that's occurring. It's not like, okay, we're going to just measure two groups and see what the brain activity is like at baseline. We want to see what's happening when they engage in some type of physical activity. Now, traditionally, how this is done is using some type of submaximal test or maximal test where they look at peak oxygen consumption, and they have these cardiovascular tests where they run a treadmill or they sit on a bicycle, and they perform these tests. And these tests, what bothers me about them is that a lot of patients can't do those tests. They're too extreme. If they try to do those tests, they would collapse. So if these patients, and they admit that the problem here is that they're only getting the mild patients in these studies. They're not getting the severe ones. So their findings are very, even if they do the 2-day test, there's not a lot of differences between patients. And this, they're onto something, but it's still not quite, they haven't figured out a way to do this. So I thought, okay, well, there's other studies that, go at it a different way, which they just use something called a grip force protocol, where they just use a hand grip, some type of hand grip protocol. In studies in mitochondrial disease and things like that, they'll use a hand grip protocol that's much more accessible for patients. It's also easier for me to administer. And I don't need a doctor standing there in case the patient collapses or something like that. I measured their brain activity with the QEEG. We did a QEEG before they did the protocol. It was submaximal grip force protocol where they had to squeeze this hand grip and relax, squeeze, relax, like that. And it was already calibrated ahead of time, so we knew their maximum voluntary contraction and all that. So we would sort of get at what is tense for them. A lot of them reported moderate levels of exertion doing this task. But anyway, so they did the test for a few minutes. Afterward, we measured the brain activity again, and what we saw was this drop in the current density. The current density, in other words, the neurons were just not performing at the same, strength, basically. So we saw this drop in activity that had taken place. And the interesting thing about post-exertional malaise, let's just take a look at this. At baseline, there's already some differences occurring in some of these bands. We didn't see differences in delta this time around. But at baseline, we saw, the cases, the red line is the cases of the ME/CFS, and then the blue line is healthy controls. And so what we found was that, they already had more current density, in their brain activity at baseline. So there was a significant differences in alpha and beta. But after the grip, you see what happened was, just looking here, so there was a shift that occurred, and suddenly there was differences in theta, and the only band that wasn't really different was delta. But just measuring like right after doing this exercise, you can see that there was a little bit further drop actually, and the cases went up. The controls went up, the cases went down. But what we did was, because the feature that's really interesting about this is that it gets worse over a 24-hour period. And it's probably more than that, but the 24 hours is the one that everybody refers to, So they'll have this crash that lasts anywhere from, 24 hours to 48 hours or longer after exerting themselves. So we brought them in the very next day, and what we found was, an even greater differences between the two groups. So what I wasn't anticipating for the healthy controls to go up. I thought they would just return to baseline, but they actually went up, and the controls and the cases, but they got worse. Okay, so all the bands, the entire frequency spectrum changed. And again, this goes to so now it's not just about hypofunction, but it's about hypofunction in response to exercise. And so they're already starting at kind of a baseline that's not great, and then they get worse. after doing this activity. So this to me really helps operationalize PEM. Now that maybe this needs some tweaking, and it needs, it could be more pronounced, but this was significant in this analysis, and patients didn't have to suffer doing it. And so this simple protocol is a way of, I think, of one way of trying to get at this problem. It was just huge, and then I did, for my dissertation, I had a larger, this was a smaller sample again. We didn't have funding for this, so we just did what we could. And then over time, I collected a larger sample of about 30, I had 34 patients compared to 34 controls. And I looked I looked at regions of the brain that are responsible for autonomic function. So when we think about the ANS and how it's the peripheral ANS is what we kind of refer to when we think about the ANS and hand temperature and skin conductance and all that. But, and then the hypothalamus, of course, has a lot to do with that. But there's also centers in the brain that orchestrate all that. And that's really, so if you've got problems going on in the brain with, let's say, there's hyperintensities going on, in the white matter or something to that effect, or there's atrophy happening in the brain, and depending on what regions are affected, it's also going to affect the autonomic system. So that's why you see a lot of people running around with, they'll say, well, I can't stand for more than a minute. My posture, POTS is called, postural orthostatic intolerance, but they're and tachycardia syndrome. So they're not able to do a lot of things that they used to do autonomically. They're having heart palpitations, they're having tachycardia, they're having other problems with the autonomic system that's dysfunctional, that's dysregulated. Now, with one of the drawbacks with the eLORETA is you can only look at cortical activity. In terms of the brain, it can only look at the cortex. It can't look at the subcortical regions unless you use something like SW eLORETA, which I didn't have at the time. So if you just look, but that's okay, because if you just look at the cortical regions of the brain that are responsible for keeping this autonomic system basically in check, right? And basically adapting according to task demands, right? Okay. That's really what has to occur. Is the adaptations, like, okay, now we're doing a hand grip, the body has to be able to respond to that and say, okay, anticipating, well, okay, what if it happens again? Okay, I'm going to actually ramp up the activity in the brain. And not only that, but I'm going to keep it ramped up further the next day, just in case, so the brain is on an anticipatory trajectory. That's really what's going on. And so I studied these cortical regions, and so I found some differences in the brain, and this was really getting down to more complexities here. But when you look at this, you can see the blue regions are the areas of the brain that, now you can look at the networks on a local level, a local clustering, or you can look at it on a more integrative level, a global level. So it's local connectivity and global. So if you look at local connectivity, there's a kind of a mixture of things going on, but you can see that there's in these particular regions like the cingulate and there's some regions in the prefrontal cortex, precentral gyrus, where preparatory motor actions taking place. That in those nodes of the brain, the size of the node is relating to the size of the amount of the loss in terms of that functioning of that network. So there's basically the network is a system, right? That's what this is studying. And there's no edges here. I didn't put in edges because it was just it makes it look too complicated. I'm just looking at nodes in this, but it's connectivity. This is connectivity. So when you start looking at systems, a new picture emerges. That's basically and then you start seeing very interesting findings in the posterior insula, which is, a lot of things are mapped to the posterior insula in terms of like your body sensations, interoception, body of all your body organs, right? Especially in the gut and places like that. So there was like this whole posterior region, which is basically less efficient going on there, less reduced efficiency going on. And so there was some compensation as well. That's what the red is showing. So the compensatory activity, that's the way I interpret it anyway, going on in some of these other regions. I'm kind of more interested in this blue part. And then you can see here, now this is the insula on the left. So on the insula on the left, when you look at this, this is, again, just baseline differences. This is not hand grip anymore, just baseline differences between patients and controls. You just see that, already in the insula, there's dysregulation going on, and that's going to affect the brain on a global level, because that's the type of analysis that we're talking about for this particular figure. So there's global and local connectivity. That means the networks are performing less efficiently, which is what's really leading, I think, to problems with information processing speed. These patients are demonstrated repeatedly to perform slower on tests of reaction time, neuropsych tests that involve some type of times element. So, and so that's really all I have for you today. As far as findings, we're really interested in doing more with. There's SW-LORETA now that is capable of looking at the subcortical structures in the brain, which is so important for some of these findings. And actually, I'm going to be doing this with long COVID as well. And I have some patients that are interested. And so we're going to do like another study and maybe look at this using an even more advanced method of looking at the brain in 3D with quantitative EEG. And what that yields even more interesting results, because then we're going to be able to look at we can even look at the cerebellum with SW-LORETA. We can see what's going on there. We can look at the thalamus, which we couldn't look at before. And some portions of the basal ganglia. So these are very important structures that more than likely involved in this disease. And so we're very interested in looking at that as well. So that's what's coming next, is just that new analysis with this, the latest developments to come out with this particular method, LORETA. So using that, it's also got more voxels. You can look at, it's higher resolution. It's got all the good stuff that you would want for an advancement, basically. So I'm really happy to have the opportunity to do that, look at that, and look at the connectivity in the brain, because that's really, I think, we're going to find some really interesting understanding. It's really about. It's not just about like brain activity going up or going down. It's about how the network is being reorganized as a result of having the illness. So it's about reorganization being changed as a result of the exposure to the cause of whatever this is. Now,
so Dr. Zinn, tell me, if you're a corporate executive, this is affecting you, the post-exertion malaise, is that like burnt out? Like you're doing a presentation and you're just like, I can't do this anymore. Because we have executives that listen to the show. I work with executives and they could be suffering from this, but they don't know that they have it. What are they feeling? Everything that we just showed, what would they be feeling to say, yeah, that's me?
The corporate executives, if they had to, first of all, when I refer to the corporate executives, they had to stop being corporate executives because they had this illness. If they had a really kind of a mild version of it, I guess they could sort of continue their work, but it would be on a more limited basis, and they would have obviously cognitive impairment, brain fog, forgetfulness, attention problems, concentration problems. You'd have problems making decisions, which is horrible if you're a corporate executive, a CEO of a corporation, you can't make decisions. So you would have that. And then you would have post-exertional malaise. That's a must. If you don't have post-exertional malaise, you probably don't have this illness. You might have something else going on. So that means that just just doing some mild exertion throughout your day would trigger a potential crash to where you would have to go lay down and recover. And that recovery period could last for 24 hours. So that's really the issue. And so a lot of patients, what they do is they figure out ways to avoid that from happening. That's really what they have to do. They have to keep, in order to recover, basically, they have to not push themselves.
Right.
I mean, and to get where they're at, they had to do the very same thing, right? They had to push themselves like crazy to become the high level achieving position that they've gotten into. They've had to, do all the hard work. So that's the idea that they're just not trying hard enough, or that they're just it's.
But they can come in. They can come in and get a 19-channel scan and show the markers just like you presented. It says there's a reason for this.
Ideally, yeah, you would be able to do it at the surface, right, at the brain surface, and not maybe have to use eLORETA. But I'm more interested, I guess, in knowing what the regions are down. So I use the eLORETA to reveal that. So, but yeah, I mean, ideally, you just do the 19 channels and just measure it on the surface and say, oh, yeah, all 19 channels have dropped as a result of doing the hand grip. Yeah, you probably have this post-exertion, which means you probably have MEC effects, in combination, of course, with other things.
One of the things that I think is on the slow burn in the background of thinking about long COVID, but also looking at trauma and the aftermath of developmental trauma early in childhood, is, if we my hunch is if we took histories of the vulnerability to people of autoimmune disorder, we know that from the ACE study, that the ACE study suggests that if you have a number of ACEs, right, adverse childhood events, experiences, you will have a greater liability to autoimmune disorder. I mean, by 20% in women, 10% in men. Okay, at a greater risk. And so if we were looking at long COVID and we're not asking the question about early childhood trauma, and this is why I want to implore you as you're doing your work to also look at the factor of setting up a system from childhood for immune collapse of some sort, and whether that's what you're looking at when you're looking at the eLORETA scan. The other thing is that is interesting to me is that I have begun to do a little bit of work with 32 channel and 32 channel Q, and you get much more refined data with 32 channel. So, and I had people I could introduce you to, if you wanted to look at other ways of looking at the brain. It might give you more data. The one other thing that I want to say is that at some point you said something about the connectivity being impaired, and their cell death was in your description, right? You said something about cell death.
Right, or something going on with the white matter where it's changed somehow. But yeah, go ahead. Yeah.
So I just want to say that could be very scary to people, and whether it's cell death or cell fatigue of its own sort, we don't know, right? We don't know really whether, like with stroke, there's cell death, but there's cell stunning that goes on that is a much larger picture in the brain and creates its own havoc. But those are not dead cells. And people, as soon as you hear cell death, people in the brain, people are going to get really scared of what's going on here. And unless that's something that I'm not aware of, which is many things I'm not aware of, so this could be part of it. I just want to make sure that that's something that they need to be worried about if they do. That it's rather than cell death, it's cell inactivity. And can we, with training, because this is what the hope is, right? With being able to get the brain to train itself into new patterns of activity, which is what we're doing with neurofeedback all the time, we could have an impact on these profound conditions. And we should be able to have an impact on them.
Yeah, I think you're making a lot of really good points there. And I think it's going to be neurofeedback in a combination of maybe something like PBM.
There's all these notes you have to hit like you did on the piano. Yeah.
Yeah, I mean, I think you're right. And we got to figure out if it does look like this is for whatever reason, this is an immune response occurring, and an inflammatory reaction occurring, whether the virus is still present in some type of really very, very minute form, whether it's, integrated into some cells actually integrate themselves into the the chromosome. There was one study that found that, herpes virus can actually invade the neurons themselves, and then they can lie dormant and then reactivate during stress. They just don't really understand the mechanisms. Really poorly understood. But to the extent to which you could train the brain to become more stable and train that metastability, because that's really what's going on, or trying to modify your activity levels and pace yourself, also getting feedback from that. So if maybe the neurofeedback you could say, okay, what you're doing is working because the neurofeedback is showing that you have less dysregulation occurring in this network. So keep it up. I think that's a really good, treatment monitoring type approach.
Well, it's a treatment too.
Yeah. And the actual treatment too.
Yeah.
There should be hopefully a way to treat the brain. I'm interested in that approach, as well as any other types of approaches that will also enhance that as well.
Me too. Me too.
So I think it's going to be a combination of approaches that will have to go after this. And certainly neurofeedback will play a major role.
I think it will. But, I also, since you're going to probably be one of the lead researchers in some of the most important areas here, right, in physical medicine, we think of as physical medicine, I would hope that you will get into your assessment this issue of early childhood trauma. So you can see if that ACEs problem is showing up for chronic fatigue, because on my hunch it is, and in long COVID, right?
Yeah.
As a part of
that's a good point. Yeah. Adverse child experiences, trauma, and setting up the conditions for the immune response would be certainly, I think that these are the other factors that have to be addressed in this illness, and what makes it so difficult to define, because there are, I think the stress response is, and the physiology involved in that is also at work here. And the autonomic nervous system and the networks that I talked about will also, those nodes are controlling the sympathetic responses and the parasympathetic responses. So these responses are not able to occur normally in these folks, or they don't appear to be, because of they're dysregulated of the particular network is dysregulated along with everything else.
The other thing that we see, typically in traumatized people that I'm training, right? So this is on a EEG, on a spectral on the EEG, not with eLORETA, right? This is not a brain map finding. This is just a everyday finding. You find excess slow wave everywhere. So what looks like hypoactivity in the brain, right? Because that's what excess slow wave should be, isn't felt as hypoactivity at all. It isn't felt like that, the physical crash, but it is felt like you can't get through your day, right? But it isn't necessarily that. At least in sort of clinical daily practice, we see excess slow wave as almost a biomarker. It's not quite, we can't quite make that claim, but there's excess theta, excess delta, sometimes excess alpha, although usually there's low alpha in these patients. It is always someplace in it's about the realm of terror. It seems to be an early shutdown mechanism in the, in childhood, early childhood trauma. This is a phenomenon of shutdown. So the hypoactivity is right, but it isn't felt in that population, in my population, it's not felt as, it's felt as sheer terror. And even dissociative events, we'll find within the realm of the slow wave activity. So the overlap is really fascinating. It doesn't mean to complicate your research. I don't want to do that. Just have to be as straightforward as possible. But just for you to know that, on the ground, there are these we're seeing this.
That's really interesting. And these are for patients that have adverse childhood experiences.
Yeah. These are developmental trauma patients. With really pretty severe histories. And their affect is fear, shame, rage, all these high activated affects. These are the problem patients. These are the patients that people turn away from, right?
Yeah.
But they're also the people who get autoimmune diseases and all other kinds of things. So they're just not so separate. But just for you to know, the marker is, at least in the office, what you're asking people to do is diminish their slow wave activity.
That's fascinating. And so that's why I'm really interested in the reactions of the brain. If you did a hand grip on those folks, I imagine, their activity would not go in the same direction as ME/CFS, or it would not be in the same brain regions, and there would be a different pattern. So I'm confident that we can sort of, again, we're just sort of figuring out how to study the brain. And it turns out that I think just measurement at baseline is good, but you also have to see, okay, well, how does the brain respond to challenges, whether cognitive or physical, when you give it, and then that's going to provide, I think, more information. And I think everybody's, individual differences. So the brain is going to react differently in some folks, and then according to the level of trauma that they've had, the level of trauma exposure, and the amount of trauma work that they've done with their therapists. So how much they've recovered from that, and all that, and whatever else they're experiencing. And then also identifying, like, what are the characteristics that are being affected? Are these adverse childhood experiences, maybe they are experiencing a level of fatigue. It's, that's a little higher than usual, or something like that.
I'm not sure. This is one of the things that I want to be in this conversation, is that I'm not sure that grip strength wouldn't show up. We've just never done it.
Right.
Yeah, we've never done it. So
And why, right?
Yeah, right. So but it's this characteristic and how of this history shows up in later. We know it by data. So is this a factor in long COVID? Is this a factor in chronic fatigue? Where is this a factor? And as soon as it's autoimmune, to me, we have to be looking at least a paragraph on whether these people met, what their ACE scores were, essentially, and that would be a great benefit to understanding how people get sick, right?
So in order for Dr. Mark Zinn to get that, he needs donations, right? Because you only
say it.
So, but I mean, hey, we're already in overtime. So, how do you accept funding? Because you only take private donations, right?
Yeah, I have been working with some collaborators to try to get grant funding through NIH. Unfortunately, NIH is very much geared toward fMRI and the other modalities, so it's rather difficult to convince them to do a study using EEG. So what we did was we said, okay, fine, we'll use EEG and we'll use all these other modalities.
Yeah.
and give them that. Well, then they start picking apart the methods and the study itself. And you just feel like pulling out your hair after, waiting 6 months.
We got to bring you back. We're all in the same boat. We just need more paddlers. Dr. Mark Zinn, what's the best way for people that never heard of you to learn more about you?
Yeah, so I do have the website. It's www.thencri.org, since it's a nonprofit organization, a 501c3 that actually Marcy set up. And so I'm just continuing that work that she was really wanting to do. And we were both wanting to do, but she had the idea to do it. I mean, it was her goal or her wish that we do something with this.
Oh, absolutely. And is it possible for the listeners and viewers, those great PDFs that you were going through, can we share that with our audience or some clips of them? So the PDFs of the studies I was showing you, absolutely. I mean, those we can share. Because I'll edit this out. We'll put that in the podcast notes. We'll put your contact information in there, and we'll wrap up.
I'd be happy to send you the PDFs of the publications.
That would we got to get the word out there, Dr. Zinn. Yeah. All right, let me wrap it up. We got to bring you back. Plus, you're in Chicago, man. We got to go see the Cubs.
I agree. I think there's.
I don't even go to see the Cubs, unfortunately. I guess I'm too busy measuring patients.
Yeah. Dr. Markson, thank you so much for coming on the show today.
Oh, thank you for having me. It's a pleasure to be here.
And then we'd like to thank you all for listening to the NeuroNoodle, Neurofeedback, and Neuropsychology podcast. We'd like to thank our Patreon business supporters because we need funding, doctor. You know how it goes. Mary Tracy's Neurotraining Strategies offers a higher standard of EEG, QEEG education, EEG clinicians, technicians, and neurofeedback practitioners with convenient online BCIA and QEEG certified didactic courses. Register now at eegstrategies.com. Please, let's help get Dr. Zinn's word out there. Subscribe to our YouTube channel. That little click and like is the difference between 3 people learning about this or 3,000. It's up to you. Pay it forward. Hey, do you have an idea for a topic or guest? Please email me, pete@neuronoodle.com. Or leave us a voicemail with the link in the podcast notes. Number 2, could you please give us 5 stars on Apple Podcasts? And Sebern will accept 4.5 stars. And hey, if you really, really like us, you can always buy us a coffee on Patreon/NeuroNoodle. Jay Gunkelman's out there dealing with Spain right now. But if he were here, you can get a lot of coverage for very little dollars on this show. Cue the music.